Still want to hear it, eh? Okay. Okay. Let me get it set up here.
Mhm.
Okay, first off, I'm gonna have to share my screen, correct?
Oh,
Okay, can you all see my screen?
yes.
Yep.
Yes.
Okay, fantastic. I don't know whether to show you these images first or afterwards. Maybe I'll do it afterwards so you have something to look forward to, because you might find this talk a little bit on the boring side. I hope not. I'm going to try to make it as interesting as I can. It's about balance, and it's what Mike introduced the last time. A few months, no, was it 2 months ago? I guess right now. And so I was going to kind of like pick up on it and maybe go into more of a deep dive on some of the technical aspects. So let me get this thing rolling here. Let's see. Start from first slide. There we go. Can you see all that?
Yes.
Yes.
You see the first slide there with the nice pictures of all kinds of balance and stuff like that?
Mhm.
Okay, good, good.
Yeah, it looks good.
Okay, great. So yeah, so the category is balance, line chokes or chokes. I guess you can say our current chokes, RF chokes. Not RF chokes in the sense of what you see in like maybe an old-fashioned transmitter or RF amplifier kind of a thing. I'm talking about chokes is we deal with antenna suppression of common mode current kind of thing. So what you're seeing in front of you there are a bunch of those kinds of structures that are built on toroid type cores, or some of them are rods, as you can see. And so there's different styles, and it's just what the choice would be depending on what the application is. A lot of times the toroids are preferred over the rods because of the fact that they retain all the magnetic flux that's generated by those wires when current runs through them, and whereas the rods kind of like leak a lot of the flux away. And so it depends, how much that's important or not. Um, to construct these things, toroids are a little bit more difficult to work with because, as you can see, you have to wind the wires or the cables around the donut-shaped object, and you have to try to get them to be spaced apart pretty much evenly, and you have to get enough on there, to make it work well. On the rods, you can see that all you have to do is kind of like wrap a wire or a coax cable around the rod, and then that's pretty easy to do and have very even spacing between each winding, and you can get a lot of windings on those things, depending on how thick the wires or the cables are. So it all depends. However, there's advantages to using toroids, and there's different materials that are used in these things. We talk about iron powder versus ferrite. So I'll be talking about ferrite mostly. I'll mention a little bit about iron powder, and then we'll get into some of the designs. And actually, what I'm going to get into is why these things work. So it'll be theoretical, and I'll show you some electrical schematics that kind of explain why these work at all, and why they're designed the way they are. So with that, by the way, these photos are the front and back covers of the book by Jerry Sivik, W2, I think it's RMI. I'm not sure what his call sign is. I have it written down somewhere on this presentation. He's a silent key. He did a lot of papers, and he wrote a couple of books on how to build balance and chokes. And so this picture comes from his book called Transmission Line Transformers. And I'll talk about transmission line transformers also. And anyway, I thought it was a nice cover to photocopy or scan and put on the presentation. So there you go. Anyway, okay, let's move on here. So, oops. So yeah, so basically what we're going to do, I'm going to start talking about the chokes first, and then we'll get into the transmission line transformers, which actually these chokes are as well. And I'll start out with the chokes because they're not impedance transforming devices, whereas the other ones I'll speak about are impedance transforming. So like we can go 4-to-1 or 9-to-1, that kind of thing. These are just 1-to-1 types of devices. So I'll just talk about them. So what you're looking at is pictures of what we commonly call the ugly balun, which is basically a length of coax that's wrapped around some sort of tube that's non-magnetic, like a plastic tube, like a PVC type of tube or whatever. And these are really popular and very common chokes. We also call current balance. And really, the picture that's in the center there is a same kind of thing, but wrapped around a toroid core. So that toroid core has, magnetic properties. It's got what we call permeability. So what it will do is it will concentrate magnetic fields that are generated by the coax, and I'll tell you how that happens. And then keep them inside the core, all that magnetic field inside the core. And the more magnetic field is concentrated in that core, the better the inductance is, and that's going to be very important. If you look at the ugly balance, let me see. Can you see my mouse arrow?
Yes.
Okay. So if you look at the ugly balance here and here, there's no magnetic core. It's just what we call an air core. So there's nothing there to concentrate the flux. What will generate flux will be current that's flowing on the outer shield. And I'll explain that. This picture over here, we'll talk about that. When there's current floating on the outer edge or surface of the shield, then you'll essentially get basically a coil, which will act as a choke, acting against that current that's flowing on the outer shield. Okay, but you need a lot, depending on the frequency of that current, you may need a lot of inductance. If you're working in the 160 meter band or the 80 meter band, and even in the 40 meter band, these things may not be adequate. They may not have enough inductance to choke off any common mode current. So that's where you have to be kind of careful when you decide to employ one of these. Versus this, which does have a lot of inductance, because now you've got the coax wrapped around a core, magnetic core. Depending on what material the core is made out of, you can develop quite a high inductance at low frequencies, and that's what you want. Because if you remember the formula for inductive reactance, it's basically going to be the inductance times the frequency. It's proportional to that times 2 pi. So the higher the inductance, the lower the frequency, where you'll get a decent reactance. Okay. And the reactance is going to be all important, because if what the reactance is going to do is going to be to choke off this common mode current. Let me explain how that happens, how the common mode current arises in the first place. So draw your attention to this figure here. Okay, this is sort of a schematic diagram of a dipole feed point. This wire here and this wire here are the 2 legs of the dipole, and they come in. This is your coax here. And so this leg is attached to the shield, and this leg is going to be attached to the center conductor of the coax. Okay? Now, under normal conditions, let's ignore this I3, these arrows on the outside here. On the inside, you're going to get a current, moving up and down the center conductor. They call that I1 here with down arrows. So this is like captured at a point in the cycle where current's moving in from this leg of the dipole down the center conductor. At the same time, you're going to get current moving on the inner surface of the shield. Now, the inner surface of the shield, okay, versus the outer surface. That current is going to be moving in the opposite direction of I1, this I2 here, and it'll be equal and opposite, okay? And it moves out, by the way, on this leg, the second leg of the dipole. Now, if these guys are totally balanced, that means that basically that this dipole is in free space. There's no metal objects anywhere nearby, not even non-metal objects, and there's nothing here to throw off the balance of this dipole. So the currents that are going to flow out on each branch of the dipole are going to be exactly equal and opposite. Now, of course, down here on Earth, that doesn't happen. It probably doesn't even happen in space either. But what always does happen is that if there is an imbalance, you're going to get a third current that's going to flow down the outer part of the shield. Okay. Now remember, why you may ask, why can you get 2 separate currents on the same conductor? So you get outer shield flow and inner shield flow. Well, the reason why is because of the skin effect at RF. So if you recall, skin effect is the fact that at RF frequencies in a conductor, the flow of the current is confined to the outer surface or to a surface in any case. So if you have the shield here, which is basically a cylinder, you can actually get current flow on the inner part of the cylinder and separately on the outer part of the cylinder without those two currents interacting at all, because they're going to take up maybe a few microns, up to maybe 20 microns or so of the surfaces, or I should say from the surface inward. So if this shield is about 1 millimeter thick, that's easily done. So these two currents can totally flow independently of each other without interacting. Now, I3 here is not at all connected to I1 or I2. I2 and I1 are connected to each other. They're equal and opposite. So what does that mean? In the absence of I3, every time you have a current flowing through a wire, you're going to get a magnetic field. So the magnetic field direction is going to be dependent on the direction of current flow. All right. So I1 is going to generate a magnetic field around the wire that's going to be, say, flowing in one direction. I2, moving in the opposite sense, will have its own magnetic field flowing in the opposite direction. Or I should say flowing, but moving, maybe rotating. So when those two magnetic fields interact, they cancel each other out, okay, because they're opposite. They equal and opposite. Now, because of that, there's very little magnetic field that actually goes outside of the shield, maybe almost nothing, ideally. So there's nothing here to interact with I3. I3 can flow freely down the outer part of the shield, and what it's showing here is this symbol here represents your transmitter. It's just a generator. And then so I3 can flow to ground. Basically what that means is I3, being an RF current, is going to radiate. Okay? It's going to radiate RF energy, and it's going to act as an antenna. That's why they say, your coax can act as an antenna if you don't have a balun on there. And that's what's going on. So I3 will actually be a antenna type current that's going to go ahead and add to these antenna currents that are on the dipole, and it's going to radiate by itself, and the radiated field that comes off this coax is going to interact with the radiated fields that come off the actual antenna wires, and then what's going to happen is they'll mix up, and you're going to have a pattern that you really wish you may not want to have, because it won't be a typical dipole pattern. So it may throw your dipole radiation off, and you won't get the radiation you expect. Aside from that, if you bring your coax into the shack, you're bringing this radiation into the shack with you. So that's the famous stories about the fluorescent lights being flickering on and off every time you key down, or you get shocked, okay, if you touch the chassis of your rig. All those things happen because of this current flowing into the shack. So that's the other reason why you don't want any of this stuff to happen. And the reason why you get the imbalance, like I said, is because this arm here sees a different environment than this arm does. So the impedance on this arm is going to be different from the impedance on this arm. Oops, sorry. How did I get that?
Yeah.
Oh, come on. I guess there we go. So that's the reason. So what happens is there's a voltage, here, RF voltage here, RF voltage there. They may be equal and opposite voltages, but if the impedance here is not the same as over here, then the currents are going to be different. And what happens is, to equalize out, one current's going to maybe more than the other current. So the excess current's going to flow out on the outer shield, and that's what happens. Okay, so you can't help the imbalance situation in most cases, but you can help get rid of this I3 by putting on a choke. Okay, so that's the basics of that. Now, sorry. All right, so I don't know what happened over here. I remember I made this talk up about over a month ago, and I haven't really looked at it much since today, or before today, and I can't remember what even this was, so ignore it. But over here, basically, what your choke's going to be is, if you wrap your coax in a coil, or even whether it's an air core or a actual ferrite or powdered iron type core, or any kind of magnetically active metal core or material core, you're going to basically form a structure that looks like this. So you're going to get, let's say this wire here represents the inner conductor and this wire here represents the shield, okay? So it's going to be, but both are going to be coiled up because because you got a structure like this, you're coiling your coax and you're forming a coil, all right? So what's going to happen is if there's a common mode current, that means the common mode current in this conductor here will be flowing in the same direction as in this conductor. That's what they call it, common mode. Because don't forget, and this is very important, we're going to talk about it, a coax line is a transmission line, all right? A transmission line works best when you have this situation down below here, when we have what we call differential mode currents. That means the currents flowing in each, say the center conductor and the shield are equal and opposite like explained in the previous slide, okay? So that means that the fluxes, as it says here, will cancel themselves out. But in the case like this, where we get current flowing in the same direction in both cases, now don't forget, there's also going to be some current trying to flow backwards in, say, branch 2, 3 here. But there's going to be also, it's going to be negated by some of the current in common mode, okay? So anytime so basically what that means is that, say the current in branch 2, 3 is going to be not the same as the current in branch 1, 4. So what does that mean? So if the currents are not equal to each other, there's going to be a net magnetic field, okay? Because the magnetic fields from these guys are not canceling each other. If currents flowing in the same direction in both branches, those magnetic fields reinforce. So if there's some current trying to flow back and is being sort of negated by some common mode current, it's going to decrease the amount of differential current or backwards current trying to flow back from say 0.3 to 0.2, and then that means that the total current here will be unequal. It may be opposite, but it may be unequal to current flowing from 1 to 4. So that's where the common mode current screws things up. It will unbalance the magnetic fields and it will cause flux to form. And what that means is you're going to get coupling from this guy, from this coil to this coil, like a transformer. All right? Everybody knows how a transformer works. So you get a transformer effect. Now, you can use that to your advantage in some ways, but really what we're doing here is when we coil, the reason why we're coiling these wires is now we're forming an inductor. I should say a high inductance inductor, especially if you've got the core, like I explained before. And then that's going to choke off because you're getting this magnetic coupling. Now any common mode current, as I said before, will be flowing, say, on the outer shield of this. This is the shield here. Sorry, the outer part of the shield here. That's going to be choked off. And then you're going to return the situation to this situation where you're going to get purely differential mode flow. In other words, current going up the center conductor and current flowing down the inner portion of the shield here with no extra current. That I3, which we don't really see here in this picture, is gone. And that's really what you're trying to accomplish. So why not just make an ugly balun and be done with it? Okay, that's fine if you want to work high bands. If you want to work, say, 40 meters on up 20, 40, 30, 20, 15, 10, and so on. It may work okay, depending on how many turns of coax you're going to have. But if you're trying to work the low bands, it won't be adequate. You need inductance here, so you have enough inductive reactance to choke off the current. And as you know, inductive reactance is a function of frequency. The lower the frequency, the lower the inductive reactance. So to aid you in that, you have to boost the inductance. Because if you have a high inductance, then you can work at lower frequencies and get a same reactance. Now the reactance probably should be in the neighborhood of about at least 2,000 ohms and higher to get a really good suppression of common mode current at low frequencies. So here, a core will help you do that. You can attain enough inductance using a good magnetic core. And in this case, you want to use a ferrite, not an iron powdered core, because iron powdered cores don't have enough permeability. And permeability is the property of the material to allow the magnetic flux to actually enter in and circulate around inside the core and concentrate itself. If you have low permeability, you won't get enough flux. But if you get high permeability, which is afforded by ferrites, then you get plenty of flux that will actually concentrate inside the toroid and then give you plenty of inductance because all the magnetic field is really confined to the toroid. Okay? And I'll get into that whole thing. But I just want to give you the basic principle of what's going on here. So you really, it's to your advantage, depending on what parts of the spectrum you like to work. If you're a low band person, you definitely want to use this kind of a choke here with having a nice high permeability toroid. All right. So there's a guy, G3TXQ here, who now is obviously silent key, who compiled a lot of these data here, Steve Hunt, in England. And he went ahead and really put together a nice chart on selection of toroids, these are basically toroids, that will give you the type of inductive reactance you need at different frequencies. So if you look down this part of the chart here, you can see that the green is the highest inductive reactance you can obtain, and the red is the lowest, okay? So he's made up these bars here at different, that represent, actually, it's kind of like a rotated bar chart. You have frequency on this axis, and I guess these, along this axis, you just simply have these different types of chokes, which he explains. He's using different toroid materials here. The material is rated by the number 43, 31, 61, okay? And then the choke, the FT is, actually, I think it's Amidon's designation. Ferrite toroid 240 would be 2.4 inch outer, I think the outer diameter of the toroid. So let's say 2.5 inch outer diameter here. They're all, I guess, and these are bigger ones here, but these are air cores. So let's talk about these guys here. So to read the chart, you can see here that he's talking about, you take a coax like RG58, wind it around 17 turns, let's say on this toroid, and these are the characteristics you're going to get of how it's going to give you enough reactance at different frequencies. So as you can see, that this particular choke gives you really good reactance, very high reactance down in this end of the band. This is probably from 80 meters on up to about 40 meters. Below 80 meters is adequate. It's about 4, according to the color chart here, it's about 4 kiloohms or better of reactance. And then when you get too low, really low in frequency, then the reactance starts going down. And the black bar here, by the way, tells you that the reactance is resistive or mostly resistive. And that's going to be important. I'll tell you the difference between a okay. I'm sorry, I'm using the word reactance. I should say impedance. Okay, impedance. There's a reactive impedance and there's a resistive impedance. What we want mostly, if we can, is get resistive impedance, not so much reactive impedance. So that means that you'll get, resistive impedance means you get mostly dissipative reactance and it's flat with frequency. Whereas reactive impedance varies with frequency and it can disappear on you. However, that isn't that big of a problem because as you can see here, you can get, if you want to work with, say, this choke, you can get pretty good impedance, enough, and inductive reactance, by the way, enough to choke off your common mode current all the way out to almost, above 20 meters, let's say. Above that, you don't get such good, enough impedance or reactance, however you want to describe it, to really do much of anything. So this choke wouldn't be useful. Now, but if you're working in the higher bands, you look at this bar here, you can see that this particular material, or making a choke by winding 11 turns of RG58 around 2 cores of this material, 52 material, you can get really nice choking action in this frequency range here, which is about, 30 meters on up to about almost 10 meters and beyond. And even all the way down to probably close to 60 meters. But below that, it's not going to work real well, okay? So that's the example of what you can do. You know, but if you wanted to make your own choke, this is how maybe the way you would do it. You would just follow these simple instructions here, and you can make a choke that will work pretty well in the frequency range you want. Let's look at the air chord chokes. This is the ugly balun style, okay? So as you can see here, none of them were going to work real well at low frequencies at all. Some are worse than others. So the best you can probably do would be maybe this guy here, 25 turns around a 4¼ inch air core of RG58, okay? That's the kind of thing that we're talking about here. So you can see for yourself that making an ugly balun really won't do you much good. It doesn't even really work that well at high frequencies. It really has this very narrow range, and there's reasons for that where you get adequate choking capability, and after that, really, you know, not much at all. So, I mean, it'll work halfway decent, but a lot of people don't know this until you look at a chart like this, and you can say, oh gosh, well, there's no point in making an ugly balun, right? Make one of these guys with an actual core, and you'll get much better results. So that's all I have to say about that. But I think it's a good take-home lesson there. Now, oh yeah, so there's you can find articles written in pretty much plain English on how these things work and how to make them. This is a very good one here by Steve Hunt himself from 2015. I can get you guys, if anybody's interested, a copy of this article. And you know, he again kind of reproduces the charts that show you, in this case, segregated out by materials and how these things function at different frequencies with these different terms of RG58 coax wound around them. So this is an example of what that looks like. Here's a 7-mode choke that's wound around one of the materials that we're talking about here. I think it's even 2 cores. You can kind of see the 2 cores connected together by some zip tie there. So it's pretty simple to make these things, as you can see. All right, moving on. Oops, yeah. So I think I explained a little bit enough about chokes there. Now let's move on to the transmission line stuff. And by the way, these are transmission lines too. Don't forget, these are, as I explained, these are transmission lines. And notice that they have pretty wide band of operation here. So we're going to explain a little bit why transmission line work better than non-transmission lines for this case. It's really going to be the bandwidth of these things. So here, these are just simple charts that are showing the basically the bandwidth of these types of chokes. These are what this is say a now in this case I don't remember what the transmission line was. The guy who wrote this, Jerry Sivik, made a lot of these cores. Here, let me go back to the picture. You can see here cores that are wrapped not with coax but with wires that are either in triplet or duplicate pairs, and we'll call a trifiller and bifiller types of windings. So in a case like this, I'm trying to see if there's over here. Here's a bifiller winding of wire that's kind of encased in some Teflon tubing, and it's a transmission line because these wires are right next to each other, and they're going to be something akin to open wire line, okay, which is just, or twin lead, which is nothing more than 2 wires that are separated by some sort of dielectric, and they're evenly spaced apart. And that's a transmission line, you know. Old twin lead that you use for your TV going to the rabbit ears is that, okay? It's not going to be 50 ohms. It'll be different than 50 ohms. But that you can adjust by simply spacing out these wires a distance. And that's why he encased them in the Teflon tubing, because that keeps the distance pretty constant between the 2 wires. And therefore, you obtain some sort of a characteristic impedance of these things. So they're very easy to make into whatever characteristic impedance you want. And we'll talk about in a minute, characteristic impedance is important. Here's another example of that. 2 wires, they're not coax. They're just like twin lead type of wires that just make, but they're homebrew. Okay, this is a triplet here, or so I should say trifiller. These are bifiller windings. These are trifiller windings. I won't get into the why there's a 3rd wire there, but there is a reason for that. Okay, so The advantages, though, look at the spread of frequency you can get. This is loss versus frequency of these things. And he's showing these different chords here, or without a core even. And you can see that the core makes a big difference, first of all, in the low frequency extension of, say, this curve here down to very low frequencies. And you get really, very good performance. You could say below 1 megahertz all the way up to almost, well, at least, through the HF band before it starts really dropping off. With these types of transmission line transform, or I should say chokes or transformers. Here again, very similar performance, except what's going on here is that you're using powdered iron here versus ferrites. So you can see powdered iron doesn't work as well because it just doesn't have the permeability to do anything at low frequencies. However, in this case, that's pretty low frequency. You're talking about going down to the 2200 meter band or something like that. You have to worry about that kind of stuff. Okay, so anyway, and that's versus this kind of a transformer. You're familiar, coupling transformer or power transformer that I'm showing here with this typical schematic, typical kind of, laminate, iron core kind of a thing. You can see here a typical frequency, I guess, versus loss or gain or whatever you want to call it. The bandwidth here is now down in the, less than 1 megahertz. You get a bandpass lower than 100 kilohertz here, so it's not useful at radio frequencies, and that's why we don't use them really for balance. Okay, they just don't work. They just don't have the bandwidth. I mean, you could do it, but you'd have to have a very narrow band that you're only worried about. And in some cases, that's in radio circuits, you'll find these kinds of transformers coupling stages. But in any case, we're not interested in that for antenna work. We're really interested in these kinds of things with transmission lines. And then you get this very wide, if you do it right, you get very, very wide bandwidth, and you don't have to worry about what band you're working on, that, to switch these out or not. All right. This is a picture of if you made a winding on your own, sort of how it would look. You have maybe 2 of the leads that are going to be grounded or something like that, and the other 2 leads are going to be used for input and output. Okay. Now, I went through I did this all by hand because I didn't have a real good way of doing, making these pictures or whatever. And then I just kind of wrote all this stuff down. I don't think I really want to go through this in that kind of detail, but I'm going to give you guys some basic pointers as to why these work. And I have, let's see, I decided to actually, we already kind of talked about that. So what I wanted to basically show you was what you've always heard about, these voltage balun versus a current balun, right? And this is a voltage balun. This is the typical 4-to-1 voltage balun that you'll buy, through, you can find it on the internet, or you go to ham radio outlet or whatever. You get these things, and really all it is it's going to be a transmission line like this, but connected in a funny way. So as you can see, it almost looks like a regular transformer, but the input here is connected to the output of this one, or I should say, the input wire here is connected to the upper side of this coil here, okay? Or, sorry, getting ahead there. Yeah, here we go. Or, and then this here, this resistor here represents the load, so that could be your antenna, all right? And as you can see from the caption here, this circuit here is actually an un-un, and then this circuit here down here is the balun, okay? So what's the difference? Well, the un-un, as Mike pointed out the last time he spoke, is really connecting an unbalanced, say, generator here, or unbalanced in source to an unbalanced load. Why are they unbalanced? Because they're both connected to ground, okay? So you have what we call a single-ended input and a single-ended output, meaning that one side of the say the source here is going to be hot, okay, is going to be generating a signal, and the other source is going to be neutral. It's always going to be a ground potential, ground voltage. Okay, 0 volts. Same thing here. This guy say like a vertical, I don't know, ground plane antenna or something like that, and so the this side of the resistor is going to be your say the vertical element of the antenna, and the bottom part of the resistor is going to be say the radial portion of the antenna. Okay, and that's grounded. Okay, in some way. That's so, and in between is going to be your coax. So the coax, the outer shield of the coax is always connected to ground. Okay, your rig here is also going to be single-ended. The output of your rig is expecting a coax connection, so therefore the outer portion of your PL259 connector is going to be grounded. The inner conductor part is going to be this part here, which is where the signal actually comes out. So this is a single-ended to single-ended, unbalanced to unbalanced, okay? And you connect the wires up like this to make that work. Now, what is going on is that the currents are forced to be equal going through this coil and going back through this coil, okay? At the same time, the voltage is going to be split. You have a voltage coming in here, and then what happens is it's not, I don't think it's marked out real well. I have it a little bit better over here. There's a voltage, say at the top of this, the bottom of this, they're going to be equal and opposite to each other, okay? And it's going to be forced to be that way, forced. So that means no matter what this RL is representing the, say, the impedance of the antenna, the voltages, let's see, how can I describe it? I probably should have put that picture of the coax connected to the dipole. If you can picture, the shield and the interconductor are going to have the same equal but opposite voltages on at all times. Okay. At the same time, the current's going to be equalized through both through both sides, and basically you're going to get, but not as strongly, and you're going to get this balun here to force the voltages either end of the resistor, which represents your antenna feed point, to be equal, equal and opposite, I should say. Okay, I kind of indicated that here. This picture is a little bit harder to look at, but V1 here and V2 would be your representing, say, the Vn, which would be the voltage coming in from the generator or from your transmitter, would be, say, the the polarity here would be plus, the polarity down here would be minus, but the magnitudes would be equal to each other. So equal and opposite voltages. Okay, not totally forcing the currents to be equal. What happens is we represent this third resistor here. This resistor here represents, say, one side of your dipole. This resistor here represents the other side. This resistor would represent, say, the shield of the coax, the outer portion of the shield. If there's an I3, we get common mode current, okay? If there's no I3, then there's no common mode current. The coils here try to force the currents to be equal and opposite if there's no common mode current. And the way to prevent the common mode current, again, is to have a lot of reactance in these coils. So therefore, any common mode current will be choked off, okay? So the construction of this balun totally depends on if you're going to use a toroid, a rod core, or no core at all, and what frequency you're working at. So again, if you're working at low frequencies and you really want to choke off common mode, use a very good ferrite toroid that has a very high permeability, maybe in the hundreds. Don't use a powdered iron core toroid because it's going to have low permeability down below 10 and won't give you enough inductance to work at low frequencies. So if you construct this balun on a good toroid, you will get suppression of common mode, and then you will get this thing to work the way it's supposed to, which means it wants to equalize or I should say, force the voltages to be equal and opposite in both legs of the of your say dipole, and this is, by the way, a balanced. This is a balun because it's balanced. You don't have a connection to ground here. You have the connection to ground over here. That's the unbalanced side. This is the balanced side because there's no connection to ground. This side of the circuit is completely isolated from this side of the circuit. So even though you've got a wire basically coiled up here, at DC, yes, the short circuit, you got a short circuit from ground to this point here. But at RF, you don't have a short circuit. You've got a very high resistance or reactance, let's say, in between here, which isolates this point from ground. So therefore, this is balanced. So that's the other reason why you want to coil this up on a nice core that's going to give you plenty of inductive reactance, I should say. Okay. And I got the math here to show why the voltages are the way they are, and why by the way, the impedance transformation is 4-to-1. Okay, it's because you get basically twice the voltage at the same current flow that comes in to the input. The current flowing through here is going to be the same current. Let's say it's I1 and I1 over here, but the voltage is doubled because now you've got the voltage across the whole antenna is Vn minus Vn, which is 2 Vin, and that's why, so you get basically a 4-to-1 transformation of impedance here. Actually, I should say the current flowing through here is half of what comes in here. So if you double the voltage and half the current, you're going to get a 4-to-1 impedance transformation, and that's why it's 4-to-1. Okay, I won't go into why. If anybody has any questions, we can talk about that. Okay, so. Again, here's an example of what we call a low frequency representation of that same circuit that I just showed you. This is the high frequency representation. At high frequencies, basically you're going to get a transmission line effect here. The transmission line is going to force the currents to be equal and opposite as best it can, and it's going to create this voltage change that will create this 4-to-1 transformation. That's at sufficiently high frequencies, assuming that there's no common mode current at all. Okay, if there's common mode current, then you're going to get at low frequencies. If they're very low frequencies, what's going to happen is you're going to get magnetic coupling between this side and this side, and then you're going to get an imbalance because the common mode current will cause an imbalance between one coil to the other coil, like I explained very early on in the talk, and then you're going to get you're not going to get the same effect anymore. You're going to basically just induce current in from one side to the other, and you will not suppress the common mode current. So let's see, coming back here. So in that case, then the system's going to act as an auto transformer. Okay, if you know what an auto transformer is, it's basically two windings, say on the same core, but there's magnetic flux between the two. This is not a transmission line anymore. This is now strictly a transformer where you're getting flux-induced current and voltage from one side to the other side. So let's say this is your primary, and this one up here is going to act as your secondary, which is where you're inducing the current and voltage into. Okay, when you get that, you can see from this chart over here that an auto transformer, sorry, where is it? Oh yeah, here. So your frequency range is not going to be anywhere near as good as if you're working in the transmission line regime, which is what this curve represents here. So you can see that the frequencies where it operates are really extended out, upwards of well up maybe around 30 megahertz or higher. Whereas this guy is going to start petering out down around 2-3 megahertz, and then start really cutting off very dramatically, and pretty much be useless from about 5 megahertz on up. So the auto transformer type, and there are balances out there that are constructed that way. And what's the difference? The difference is that you're not using, say, a bifiller type of winding, or you're not using a coax. You're just using a single wire, okay, wrapped around a toroid. And then the other wire is wrapped around maybe the other side of the toroid, and then you get just a simple transformer, okay, and then there you get some, it may work as a choke, but it's not going to have a frequency range that maybe you're looking for, so you want to try to avoid those. And there are some on the market, and I don't know the brands, but they are constructed more or less as an auto transformer, and they really don't work all that well, okay, because the people who make them don't understand what a transmission line transformer is. All right, so I think you understand maybe enough about that where I can move on to the next slide here. Um, oh, sorry. So, okay. Um, yeah, I don't. Yeah. So okay. The other aspect of these is that the transformer needs to have characteristic impedance of a certain value, and not only that, but the winding length should be a certain length too to make it work well. That's not so much shown here, but basically the rule of thumb is that say for the if it's a 4-to-1 balun, that the characteristic impedance should be about half of what the load impedance is. So if you're talking about a 50 ohm load, that means the characteristic impedance of your transmission line that's wound around that toroid should be about 25 ohms. Okay, and that's shown here. So then you have to do some tricks. Maybe if you're using say RG58, you may want to have two windings of that and then parallel them so you get the 25 ohms as an example. Okay, there. How critical that is? It's not super critical. It's just a question of the power transformer, or sorry, power transfer. Of course, if you get maximum power transfer, if this kind of rule of thumb is kind of respected, and this, by the way, this number will change if it's a 9-to-1 balun, let's say, then that's instead of 2, you would divide by 3. So you'd have say 450 ohms divided by 3 to give you about 150 ohm characteristic impedance, and that's something I had to do myself when I made a 9-to-1 balun following all this stuff. Anyway, I just showed this chart here that you can actually, if you want to make a bifiller transmission line, they got a chart here of what the characteristic impedance would be based on the wire diameter and the spacing between the wires. So you can actually show that this shows that you can actually, if you can say use number 14 wire spaced out about what, 70 mils or 65 mils apart here, you get about 25 ohms impedance there. And then if you want to increase that, you just decrease the wire diameter. Or if you want to say use number 14 wire because of power considerations that you're pumping through, you may want to change the spacing here a little bit. And then you can get the characteristic impedance you're looking for. Anyway, that's just to give you an idea about that. Do you have to do that? Not really. You don't have to do that. It's just that you'll get maybe a little bit better power transfer. But if that's not a consideration, then it's not going to really be important. You can still use, say, 50 ohm if you're say doing a 4-to-1 balun here. You can, and you're supposed to have 25 ohms. What if you don't do that? What if you just use 50 ohms? So now the characteristic impedance is the same as the load impedance. Is it really the end of the world? No, it'll still work just fine. Maybe not as best as it can work, but it will still work. And it will simplify the construction of these things. Anyway, so that's just the other point, that the characteristic impedance of the transmission line should work. Also, the other thing is that the total length of the winding should be probably at least lambda over 8 of the highest frequency that you're going to be working at. So for instance, if you're working, the highest frequency you're going to be working at is say 10 meters, okay? Then lambda over 8 is approximately a little bit over 1 meter, 1.25 meters. So that means your the amount of transmission line that you're using should be about 3 feet long, a little bit more, maybe almost 40 inches long. And you wind that around your toroid. So you can see why you need a large toroid for that. One of the reasons why you need a large toroid for that reason is so you can accommodate about a yard's worth of transmission line. And RG58 is about as thick, if you're going to use coax, is about as thick as you're going to want to use because of the spatial constraints, and also being able to get a decent amount of power through it as well. Okay, now let me see what else I got here. Sorry, going the wrong direction. One last thing, there's something actually called a current balun, which is also not just a current balun, but it will do a 4-to-1 impedance transformation as well. There's also 9-to-1 impedance transformation current balance. What these do is they're going to force the currents to be equal in each branch of, say, your dipole, okay? And without really forcing the voltages to be equal. But what's more important, current equalization or voltage equalization? Well, if you want to reduce any chance of getting common mode current, you definitely want to force your currents to be equal. Okay, and this kind of a balance going to do that. All right, it's a balance because, again, single-ended input, but balanced output here, balanced load, no ground connection here. It's not an unun. Over here, I show an unun in this for the same type of configuration. Even though this looks different, this circuit and that circuit are the same thing. It's an unun because you can see blurry here that there's a ground connection at this point. There's also a ground connection here near the source, near the generator. So this is an unun, okay? And over here, you've got the Balun effect, okay? The load is, say, a dipole antenna that's not grounded at all, and the source is grounded over here. So if you're working with a vertical, let's say, or any kind of grounded antenna, end-fed, Windhams, those kinds of things, you're going to want to use an unun here or here. And if you're working with dipoles or any kind of balanced antennas, quads, that kind of thing, loops, you're going to definitely want to use the Balun, and that's where the understanding of what an unun versus a Balun is and what they're used for. This guy here, I won't go into why it works. I got all the math here, but basically it is going to force the currents, not the voltages, to be equalized. And so in this case, you're interested in suppressing any kind of common mode current, which it will do very nicely. At the same time, it will do a impedance transformation. So therefore, you can go from a high impedance, say, feed point here to a 50 ohm line. If it's a 200 ohm line here, you'll have 50 ohms over here. 200 ohm line may be a folded dipole, I think, or other types of antennas. Maybe some sort of non-resonant antenna where you're going to get fairly high impedances at your feed point, and you want to transform those down to 50 ohms. And this kind of Balun will work in that case, or in the case over here, and you'll be able to suppress any common modes at the same time. So there you go. I think we're near the end of the talk here. And I said that I had some more interesting, gosh, I'm going backwards. Let me just see here. The wrong direction. One sec. Come on. I have to use the key. Here we go. Here, I want to show you guys something interesting. On my, this is a whole different topic now, and one of the reasons maybe it's not really related to common mode currents and balance, but it is related to broadcast interference. That's coming in very, very, very strong at my location. I've gone over this with Don Reed and Ron Davis, who Ron Davis was very close by to me, and Steve. I don't know if you have seen this or gotten any kind of weird effects. This is my monitor showing the output of my SDR play with the SDR Uno software running it. And this is showing this weird stuff going on my 80-meter reception, and I'll even show you 160-meter reception, that I'm getting this weird broadcast interference. And
I'm not having that problem.
Sorry?
I'm not having that problem. I guess being a block from you is enough, but
well, here's the deal. This is I even have a video clip of this so you can hear the audio. But what's going on is this is station Kloo AM, KLOO AM, which has a broadcast tower out near HP on the Highway 20 and Circle. And they're booming in. I don't know what's going on. This just started happening over the weekend. Literally, this never happened before. And what it's doing is getting into my front end of my receiver. I mean, it's really weird. I don't know why Steve, you don't see it. Ron doesn't see it. I don't think Owen would see it. I don't think anybody has seen this except me.
You're just lucky.
I'm sorry?
You're just lucky. I had a problem. It wasn't broadcasting, but a lot of interference, and it went away when I replaced my washing machine. But that was a different issue. But
Okay.
yeah, I haven't seen that. I'm using my primary software for my Anon, for instance. I use SDR console, but I've got the SDR Uno. I haven't loaded that for probably a couple of years now. But and
Okay.
I also have an SDR Play, so I'll take a look. But
Yeah.
I've not experienced that.
Okay. This is what's happened the other night on the 40 meter band. You can see this line here. That's the carrier of the AM signal. Um, and you can hear I got this thing on AM mode here on 7.107. It's coming in now. Also over here, I don't know why I didn't flick the over here too. Same thing. And um, if I play, I'm sorry you can't hear the audio, but that's actually Clue AM. So they're playing. I mean, it's just coming right in. Not so bad on the. It's also over here on the edge of the 40 meter band, right down near 7,000 or 7 megahertz. That's all part of that. So you're seeing the modulation going on here. You don't see the modulation so much over here. That's on 40 meters. So even on 40 meters, I get it. And it's really annoying as hell. Um, and it's creating a lot of background noise. You can see the background noise on the waterfall here is just really sky high.
Is
Um,
this time of day related, or is it always that way?
no, it's always there, and that's the thing. It's not a skip, and it's very localized stations. Also, KJOE, the Beaver station, KJOE, which is real close to where I am too, is mixing in with these signals. And so what's going on here is basically, look how strong. See, it's very intermittent here. The strength of the signal here, just coming up here now, and you can almost start hearing the modulation. So it's broadcast interference and it's creating all kinds of spurious mixing signals and getting in all over the place. Um, Fortunately, not so much in the high bands, but definitely down here, 40 meters and below. I'm seeing this stuff. So the weird thing is nobody else seems to see this, and I have no idea why. Why am I the only one? And it just started happening over the weekend.
Well,
So,
I have a couple of comments there.
okay.
So this looks, there's a couple things. First of all, when I saw the pattern, it looked like some kind of a switching transformer. I know I have a battery charger that uses a switching regulator that will create this pattern. But being that you say that it sounds more like it's a mixing problem with other AM broadcast stations mixing into it, I would expect it to change the amplitude in nighttime, because there they end up reducing their transmit power.
Uh-huh.
The typical thing that happens on that is that it is some kind of a ground, metal ground somewhere that has oxidized and has rusted and is now creating a diode, which is creating, allowing it to re-radiate that AM signal close to you. And then you're also saying that it's something very close. What would be really interesting is take your little SDR Play and your laptop and drive away from the house and see if it disappears. If it disappears, you come back to your house, it reappears, then take that, and if you can, walk around the yard there and see if you can try and localize that system or the intensity of the signal there. It can be a aluminum rain gutter. It can be a chain link fence. It can be, I don't know if you have a tower there. It could be bolts and nuts on a tower. But it looks to me as if it's something that you're getting a diode effect from a poor ground connection that is allowing that energy to be re-radiated locally.
Thank you, Mike. Yeah, I've heard of that happening, and I'm suspecting that too because the fact that nobody else nearby me is getting this effect it makes it look like it could even be part of the antenna system itself that's doing this. Maybe something rusted, along the way, and it's creating a diode.
Yeah, because another one is like if you have coax cable that either your transceiver is not grounded, or coax cable that is not terminated, sitting there floating loose,
Mhm.
that can also cause some problems like that.
Yeah, okay, I'll definitely, because my next step was to make a broadcast interference filter, which basically is a high pass filter that cuts out above, or actually cuts out below 1.7 megahertz, the top of the AM band. Um, but I'm gonna do what you said and see if I can just find maybe something, like a rusted part or corroded part
Yeah.
somewhere around there that might be causing this. So you're right. But it's very strong, as you can see that picture there on the 80-meter band was taken the night I was working the, what was it? I guess the CQ DX CW contest. And I'm sorry. No, well, no, I remember which contest it was, but maybe it was the ARRL contest. It was, so you can see the world map there with the gray line, the Terminator.
So, so Scott, a broadcast filter will not solve your problem.
Yeah.
What's happening there is that is signals being mixed together and being re-radiated at a different frequency, and you can see the broad spectrum of that frequency.
Right.
It's covering up all your 80-meter band. And so a broadcast filter is only going to knock things down from 2 megahertz on down through the AM side of things. It's not going to get rid of your problem about that signal being re-radiated at your 3.9 megahertz in your 80-meter band.
I understand. Because I thought maybe it was just a front-end overload, problem from the strong AM broadcast. But if it were, I think other people would have seen this the same effect, especially Steve and Ron, because it was so, and Olin as well, because, we're all in the same basic area. And we would have been hit by a very strong AM broadcast signal. So you're right, Mike. It probably won't do me any good. I'm sure it's coming from something, close by the antenna, but definitely actually literally broadcasting in those frequencies.
Yeah. So now you have a nice picture using an SDR. Do you also see the same problem in any of your other receivers?
Well,
Good
yes.
question.
Yes, I do. I do. Yeah, I'll answer your question, but yeah, just to answer what Mike just asked. Yeah, I do. It's my ICOM 706 is also seeing the same, or I hear the same stuff out of that. So it's not a question of digital versus analog. I'm sorry, it's not purely a digital problem. It's definitely there. It's definitely something real that's not an internal digital glitch of any kind.
Yeah, and it's also also reduces the likelihood that it's an overload issue with the SDR play.
Okay. Yeah. Right. Yeah. Somebody else had a question.
Well, I had a question. Is your grounding system all bonded together? You've got, the service entrance ground and your whatever ground rods you have, are they all connected together?
No, they're not.
Ah,
So you think that could be one of the issues?
it could be, but I could defer to Mike on that. But
Okay, well, I'll try everything. I mean, grounding, proper grounding, and looking around. I think what Don offered me his ACO 817 because it's a small rig. I can walk around the property and try to look, see if I can pinpoint. And plus, he's got a direction finding antenna on it, so maybe I can try to pinpoint the source that way too. But I will definitely try all these tricks. I suspected it might be something like a diode, something like a rusty piece of metal that's causing this, because I've heard of that happening, and even people who have sometimes tooth fillings will do the same thing, and you can get radio stations playing in your mouth. So, yeah.
do you have which floor of your house? You've got 3 stories on your house. So which floor are you on?
The bottom. Bottom. It's a semi-basement where I am.
Okay, yeah. I'm on the ground floor also, so that makes grounding a lot easier.
Yeah. So I'll definitely, I've been wanting to do the grounding. I'll definitely do that. I'll tie up all the, everything together and lead it out to a ground rod, which will be tied to the house grounding system, and see if that also helps to solve the issue. But yeah, it's very interesting. I just thought I'd show you guys because, first of all, I wanted to see if anybody else possibly has had this problem, and secondly, I just wanted to show you what really weird signals can do to mess up your reception here. And I like working low bands, so this picture you're seeing here on the 80-meter band is also kind of reproduced on the 160-meter band, but even worse because the signals are seemingly stronger. And I was wondering if that's even some sort of a harmonic effect too. But anyway, you get those three big peaks like that, and so forth, and all those little other peaks there are actually seemingly weaker stations, or maybe they're just the same station but just lower harmonic or lower components of the mixing process. So there could be a lot of weird mixing going on even. And I thought it was also an intermodulation problem too.
Did you get all the turkeys out of your antenna?
Yeah, they're not responsible for this. The other, yeah, because it's actually two stations. It's mixing Clue AM, which is on I think 1340, with KJOE AM, which is on 1240, 100 kilohertz apart. So those two stations seem to mix together, and I'm getting, like, when you listen to any one of those signals there, you actually hear both the audio from both those stations mixed together. So it's very weird, very interesting. But anyway, maybe next month I'll show you guys the solution to the problem. Anyway, okay. So I'll stop sharing my screen. And I thank you for your attention on this. Wait, let me get.
And thank you, Scott, for all of this. This actually fills in a lot of cracks and crevices that I've never got around to try and explain.
Oh, sure.
But that was very good as far as all the fill-in works that kind of explains in a little more detail on how and why these Unums, Baluns work, and how you apply that technology to different kinds of antenna that you might have deployed. So appreciate that.
Oh, my pleasure.
Thank you, Scott.
Excellent job, Scott.
Thank you.
Thank you. I just wanted to kind of give I know it was a little on the technical side, but I thought, it was, like I said, it was a deep dive to kind of go in there and look, like, say, why do these work the way they do? Why are they coiled up? Why are they this? Why are they that? And then, obviously, we're all going to go out. If you're going to get a Balun, most of us are going to just buy one. And so you just kind of leave it up to the manufacturer to make them. But there's so many Baluns on the market there, and you kind of don't know, really, is this one Balun better than another Balun if you buy it, say for $30? And you want to, if you're going to spend the $30, you might as well make sure that you're getting a good one. So just make sure it's a transmission. It's definitely a transmission line Balun, and it's on a nice core, which they're probably going to be a good ferrite core. I don't think anybody's making them anymore. I think that the guys who made, not very good Baluns probably got weeded out by now, and everybody who's selling them on eBay and Amazon or through HRO, like Radio Waves, those kinds of companies, are making pretty good Baluns. So I don't think there's that much of a difference in manufacturer anymore, because the ones that are making good Baluns survived the market. How the forums kind of can trash a product, and I think the bad stuff got trashed, and those guys went away, and the good ones are left, because they've been making Baluns for decades now. I mean, it's nothing new.
Well, it's so easy to make yourself. I started making my own Balun in about March of 2019, and I was surprised. Other than it's hard on your fingers.
Yes.
But apart from that, and with the electrical box that you pick up at Home Depot, it's really straightforward. And then you know what you got.
Yeah, that's true. The other thing is, if you're working with high power, you just have to know. One thing I didn't get into was the size of the toroid. Or I should say the power levels that you're putting through will determine sort of the size of the toroid. So at 100 watts, it's a question of the saturation of the toroid material and by the magnetic field that's generated. And so if you've got a large toroid, say the 2.5 inch, outer diameter ones, those can pretty much take a lot of power because they will not saturate. You don't want your toroid to saturate out. That means that it won't respond to the magnetic field after a certain level of magnetic field, and that has to do with apparently it has to do with the size, I guess, as well as the permeability, but mostly the size. So the bigger the thing is, the less, the more flux it can take before it will saturate. And so if you're working on a kilowatt, I don't know what you do. I guess you have to do multiple. They have to make the balance out of multiple toroids, let's say. So you have like four toroids kind of stacked together, and then you got plenty of material there that will not saturate out at, say, a kilowatt or 1500 watts. But if you're working at 100 watts barefoot, say normal rig, then one of these 2.5-inch outer diameter toroids should be plenty. You won't have to worry about saturating. Also, the toroid material can heat up, and that's another factor. So the materials that, say, were shown on that chart I showed you would be good materials that really won't heat very much. Some of the other materials would heat up pretty quickly, and you can actually crack the toroid because it gets too hot and melt the insulation on the wire and so forth.
One other thing I'd point out is buy your toroids from a primary distributor like DigiKey or Mouser, and because then you're getting A quality, right? Ferrites right from the manufacturer. Don't go to the secondary market like what am I thinking of, the one that's pretty popular, but he's selling seconds. So
yeah, I bought mine actually through a place like that. I think it was something Supply. I can't remember what it was called, but and they had defective one, or not defective, but there were defects on them. They weren't like perfect, and they had little pits or whatever.
Yeah, seconds. Yeah, they were.
And I bought those, and then the idea was that I see, the thing is, yeah, you're right, Steve. I thought, well, it's like, you go to the store and they're selling a piece of furniture that has a scratch on it for half price. And if you don't care about the scratch, you buy the piece of furniture and it's going to be just fine. Well, in the case of these toroids, you're right. It could be not just the fact that they're scratched and they're going to sell them for a reduced price because they're physically different, slightly deformed, but they're still going to work the same way. It could also be that the quality of the material, the powder or the ferrite material that they put in there, maybe it wasn't mixed right. Maybe it just wasn't made properly or perfectly, and then they're not going to be what you think they are. And so I guess the bottom line is, if you really want to get into it, you can be very technical, and you can actually measure the permeability of these things when you get them and so forth, and know exactly what you've got and what you're working with.
I found that the price through Mouser, for instance, was actually the same or a little bit cheaper than getting one of these.
So I found that. Go through Mouser, DigiKey, or Newark, or any of those catalogs, and you can get good stuff. Yeah, and it's not any more expensive, or like you said, even cheaper than through these other supply houses that sell the seconds. That's true. So anyway, so that gives everybody basic, sort of basic idea on these things. The basic bottom line is, if you're going to use the ugly balun idea, if you're working at say 20 meters or 10 meters or something like that, that's fine. But if you're going to, and even then it may not work very well, according to that chart I showed, you're best off not going that route. It's probably, you have to wind a lot of coax around a big old, piece of PVC pipe, and it's a big hassle, and you have to, make sure all the windings are close together and all that. And it's really, I try to make those things, and it's not easy to do. And they don't work that well anyway, so don't bother.
And those are primarily chokes anyway, not baluns. So
yeah, exactly. They're just chokes, and they don't. And like again, they're most likely not going to work that well for you. So, maybe at 20 meters, yeah, okay, but not in a general sense if you want to work different bands. So, anyway, okay, so that's my spiel, and hopefully next month, or not. Are we going to have a meeting next month? By the way, Anthony, I forgot what you said.
Christmas.
We will have the Christmas.
There will be a meeting.
We're not going to have a presentation or anything like that, right? It's just going to be the fun stuff, right? Kind of a virtual fun.
Well, this was fun, Scott. For us, anyway.
Okay. But yeah, I'll show you guys what I come up, if I solve the problem by then, which I hope I do, because I really would like to use those lower bands at my location, my QTH. I'll show you how I went about solving. or searching at least for the source. And so thanks to Mike and thanks to Steve, we'll follow up on those clues and see if we can find some weird natural diode out there that's, from a corroded piece of metal, which
So-
it could well be.
Yeah. So one final comment here is that Crew 1 on board the SpaceX Dragon docked at the International Space Station a little bit less than 30 minutes ago.
Great.
Excellent.
And so they probably another half an hour or so before they open the door, the hatch door on it.
Fantastic. So I understand the stage was it stage 1 of the rocket was returned to Earth?
Yes, it was.
Yep.
Mhm.
Yep.
Yep,
Yeah.
on the, yeah. And that's going to be used in the next Crew Dragon
That's
launch.
That's great. All right.
It's been one of the. I remember they lost one of the first stages in like July or August
Right.
due to a reignition issue, and the commentary from one of the articles I was reading about it was like, keep in mind that like 3 years ago, trying to land a rocket was an insane idea. And now we're upset that we lost one that didn't quite make it back. Like,
Yeah.
Yeah, well, think of the early days of rocketry in general. How many of these does there were? But yeah, this is now, going into the realm of the old science fiction stuff where the rocket would, be able to land and take off and all that stuff. So now we're into that type of technology, which is fantastic.
yep. All right. I think that's about all I had. I was gonna mention the dragon there, but Mike beat me to it. So, so just remember, work on your themed backgrounds and or sweaters for next meeting, and I'll try and stick more towards a social theme, and hopefully have a good turnout. Till then, stay safe and stay sane, I guess is the
Yeah, that's
the call right now.
Yeah. We'll check up on Johnny.
Yeah, I think I'll try and shoot Chris an email here in a little bit and make sure he's doing okay. So
Yeah, definitely. I haven't heard him either lately. So, okay. Okay, guys, have a good month, and we'll see you. When is the next meeting? On December?
let me pull up the calendar. So it appears to be the 21st.
Okay.
Well, guys, stay safe. Wear your masks.
You too, definitely. I'll see you around, Steve.
Okay, Scott. Hey, I got my antenna back up, as you may have
I
noticed.
saw. I noticed that. It looks really nice. That's great. All right. Yeah. See if you check on 80 meters and see if you see anything weird. Okay. Anything.
I'm gonna do it right after this meeting.
Yeah. Just see if anything looks like what I showed you, even in
Okay.
tiny little peaks. Okay. All right, guys. Have a good evening. Talk
Good
to you
night.
soon.
All right, good night.
Mhm.
Good night, everybody.
Take care. Good night, all.